My name is Justine Olshan. I've been working at Confluent for the past 3 years, and I'm also an Apache Kafka committer and PMC member. My presentation today is on transactions in action and the story of exactly once in Apache Kafka. Over the past year, I've been working on transactions, and there's quite a rich history in Apache Kafka, so I'm going to start from the beginning. So before we even get started with any of the historical context, I want to go over a few key terms. And the first is, what are transactions? So transactions are a sequence of operations in which we want all of the operations to be completed or not be completed. We don't want to have it in this state where some are completed and some are not. It can leave us in an inconsistent state. So the classic example I always like to think of is perhaps you're doing some monetary transaction where you're taking money from one account and depositing it into the other. You don't want to have some state where you remove the money but didn't deposit it in the other. You want to make sure that both operations occur or neither of them do, so you can retry. So it's all or nothing, basically. And another way of phrasing this is an atomic operation. This is a super well-known concept in databases. I won't bore you all with the gritty details, but we were also wondering if there's something similar in Kafka. And originally when Kafka was created, there wasn't such a thing. But there was a use case for it, right? We could see a similar use case where maybe we want to write into two partitions atomically. And another common use case was in streams, where maybe we want to read from a partition, do some streaming processing on it, and then write to another partition, and we wanted that to occur atomically. The idea about transactions is that we expect failures, right? If it was a perfect world, we could just read and write, and we wouldn't have to worry about leaving things in an inconsistent state. And so the important thing about transactions is, how do we handle these failures? So the next thing I want to cover very briefly is exactly once semantics. So before I get into exactly what exactly once semantics is, let's go into kind of some subcategories of semantics. So one is most once semantics. And this is where we will have some operation occur at most once. So it could be 0 or it could be 1 time. This is kind of like a fire forget notion where you just send it and then maybe it does go through, maybe it doesn't. Then there's also something known as at least once semantics. This is when we write it at least once, but it could be more times. So one way I like to think about this is that, it could not be more than 1 time. Let's get that clear. So the at most once semantics, we could have duplicates. We could have more than one. Or we could not. Okay, I'm confusing myself. With at most once semantics, we have it at most once, so we cannot have duplicates. But in at least once, we could have duplicates. So if we combine these two, you get exactly once semantics. So at most once and at least once, we get exactly once. So I guess the way I kind of like to think about this is, with exactly once semantics, we have this no duplicate policy, and we also have this kind of idea of ordering, because when you have at least once, you kind of don't want to process anything new until you've ensured you processed everything at least once. So ordering kind of comes naturally. Finally, I want to go over idempotency. So idempotency is when an operation can be performed multiple times and will always result in the same outcome. I like to think of my computer science 101 examples here. We have like an assignment to x equals 20, and then we have this unary operator x plus plus, which is like the same as adding +1 to x and assigning it. So if we executed this first operation, x equals 20 multiple times, x will always equal 20. But if we do this x plus plus multiple times, then we will continuously increase x. So this x plus plus is not idempotent. And how this kind of extends to Kafka is that if we had, an idempotent producer, if we tried to produce to the log, we wouldn't see any change in the result, even if that was received multiple times. So that would be kind of a cool property to have. So back in the early days of Kafka, the question was, can we have transactions and EOS in Kafka? There's a super, known need for this. And that's where we have KIP 98. So I have displayed this beautiful diagram of KIP 98, and I've included the link. I will go into a little bit more of the details over the next coming slides. So how do transactions work in Kafka? Let's start with the key players. So the first player I'd like to introduce is the producer. The producer is the writer and kind of the person who is producing all the data to the transaction. There is always one producer in a transaction, a single writer, and they have a unique transactional ID. This ID is used along with a producer epoch that is bumped on errors and when a new producer starts to make sure that we fence old zombie producers coming through or any old requests that had previously seen errors. So the producer will add data, they might commit offsets, and they're the one who decides when they're ready to abort or commit the transaction. Next, we have something known as the transaction coordinator. The transaction coordinator is a broker on the Kafka cluster that is assigned to the producer based on the producer's transactional ID. The transactional coordinator is responsible for storing and persisting the metadata with respect to that transaction. So any partitions that may be included in the transaction, when it was started, all the important metadata. And the reason why we persist to disk is that if the transaction coordinator fails or we have to move to another broker, we can reload that state and continue with our transaction or abort it if necessary. The transaction coordinator is also responsible for sending the markers to all the appropriate data partitions because it is the one who's tracking all of the participants, all of the partitions that are part of the transaction. Finally, the transaction coordinator may also call off the transaction if it's been ongoing too long. I think this was mentioned in the keynote that after a certain amount of time, the transaction is automatically aborted by the server. Next, we have the brokers that are hosting the data partitions. These are just the brokers that contain partitions that might have transactional records. And those transactional records also have unique producer metadata that is important for the idempotent producers. I'll go into this a bit more in the coming slides. Finally, we have group coordinators. So earlier I mentioned that we might want to have a use case where we read, do some processing, and then write to an output topic. In that case, we need to commit offsets, and the group coordinators are responsible for that. So if we wanted to commit offsets as part of the transaction, we'll need to write to the group coordinator's consumer offsets partition. So they might be an optional transactions participant. And they're kind of similar to the data partitions in that you will write information to them about the transaction. This is supporting the streams and read and write EOS applications I mentioned before. So just a high-level overview again. The producer will initialize a transaction. It will produce data by adding the partition to the transaction first, and then producing data to that transaction, or to that partition that's part of the transaction. The producer may also add offsets, and then when it's ready, it will request to abort or commit, and then the transaction coordinator is responsible for sending out all those markers to the various partitions. So here's this beautiful diagram again. I'm going to quickly go over the steps in a bit more detail, just to get into the nitty-gritty a bit. So step one, the producer, when it comes up, it actually must find the transaction coordinator that it needs to talk to. And how it does that is requesting any broker sending its transactional ID. That broker will respond with the transaction coordinator the producer needs to talk to. And then from there, in step two, the producer ID will send, the producer will send a init producer ID request to the transaction coordinator. The producer ID is a server-assigned ID that the transaction coordinator and the broker and basically Kafka cluster uses to track the idempotent producer ID state. The producer ID and transactional ID is a one-to-one mapping. The transactional ID is supplied by the client and the producer ID is supplied by the server. If there was any previous ongoing transaction or knowledge of this producer, we will also bump the epoch on this init producer ID call. So once the producer gets the ID, it's ready to begin the transaction, and that's step three. It's not marked on here since it all occurs inside the producer. When it's ready, it will, set up the metadata it needs, and then it can start the produce loop that is part of the transaction. So that's step 4. So with step 4, when we're ready to produce to any of the partitions, we must first add them to the transaction before we can produce. And that's 4.1. So we'll send this request, add partitions, to the transaction coordinator. Then in 4a, we are persisting this transactional, persisting the partition to our transactional metadata topic. We also persisted our producer ID to transactional ID mapping. Then once we've added this information, we will go and send the producer request to the broker like normal. And in our little state, we will include a sequence and the producer ID inside the record batch of the transactional records. Similarly, if we wanted to add a consumer group offset commit, we will send a similar request to the transaction coordinator to add that partition, and then we can add the offset in 4.4. It's also persisted to the log. Okay, so we've done this loop, we've produced to all of our partitions. Now we want to finally commit our transaction. So that's 5.1. We'll send an end transaction request, either with a commit marker or an abort marker. When the transaction coordinator receives that, it will actually write a record called prepare, and it includes the producer ID. This record is necessary for when the transaction coordinator perhaps fails over and comes back. If it sees that this prepare marker has been written, it actually will go ahead and send all the necessary markers to the partitions as normal. So it's not quite the same as the prepare phase in two-phase commit if you're familiar. It's already in the process of actually doing the commit or abort. Once we've written this record to our log, the transaction coordinator sends all the end marker requests to the group coordinators or the brokers that have been added to the transaction, and all of the partitions will have their commit or abort marker written. When that is finally complete, all of the responses will come back to the coordinator, and the coordinator can finally write the commit or abort marker for the transaction. So just zooming in a little bit more, since I didn't fully explain everything here, in the transaction coordinator log, we have records written when we do our init producer ID to have the mapping of the transactional ID to producer ID. Every time we insert a new partition into the transaction, we'll write a record about that. We'll have our prepare records and we'll have our commit records. In the data partition, we'll have records of all of our different messages with a sequence ID and the producer ID, and we'll also have commit markers for the ends of the transactions. And similarly, in group coordinator, we'll have our partition, our offset, and the producer ID, and we'll have commit markers. Okay, so I gave a high-level overview of transactions, but I didn't really explain about the ordering or duplicates and the idempotent producer. So let's go into that now. So each message, I did say, has a sequence number assigned to it from the producer. And the broker is keeping track of all of the last 5 batches that it sees. And the idea here is that if you have a new request come in with the same ID or the same sequence number for the same ID, we will reject it as a duplicate, we'll send a response, we won't write it to the log. However, if it's not in the next sequence, let's say it wasn't in those last 5 batches, it's just some other sequence, maybe way in the future or way in the past, we will also reject it and return an out of order sequence error. So the idea here is that we cover the no duplicates case with the storing the last 5 batches, and we ensure any other ordering with this out of order sequence. And so the question is, okay, we have the ordering and duplicates, do we guarantee the idempotency? And while KIP 98 promised EOS, there were maybe a few edge cases that were missed. So KIP 185 was the first KIP that tried to introduce idempotency as the default for our Kafka producers. And there were a few issues that kind of slowed the KIP down. So one thing was that the out-of-order sequence error was a little bit ambiguous when it was first introduced. There were a few scenarios that were maybe real data loss or retriable or maybe unclear, and they were all seen as fatal. So an example of real data loss would be if we saw sequence 5 come in, sequence 6 suddenly, disappeared, and then we try to write sequence 7, we lost sequence 6. That's real data loss. But there are a few other cases. So maybe a retriable error could happen to sequence 6, and it's in the process of retrying. We want to have sequence 7 also have a retriable error to give time for sequence 6 to come in. So in that case, we don't want it to be fatal. We actually want, the sequence 7 to be retriable. And finally, there were cases where maybe we don't know what happened to sequence 6, and we might want to wait, we might not. It was just very unclear. And so in that case, we also maybe didn't necessarily want to see a fatal error, because then we have to restart a producer. We might have to restart our application. It was a little bit not great. And so Kafka 5793 tried to address some of these known scenarios, maybe with retention issues or retriable errors. So the idea of this JIRA was basically to have out-of-order sequence represent real data loss only. And we introduced this new error called unknown producer ID to cover retention errors. And when we got this unknown producer ID, the idea was that we would bump the epoch and reset the sequence. Just quickly going over the retention errors, we were storing all of the producer ID data in the partitions records, right? I mentioned earlier on the slides, in the transactional data, we have some producer ID state on each record. And this state in the records was loaded into the broker in order to do the sequence checks that we mentioned. But as you may know, Kafka doesn't store data forever, and so eventually some of this data is removed for the various retention policies that we have. And when this happens, we might lose that sequence information that we need to correctly identify what scenario we're in. And so this idea with unknown producer ID is that if we remove this data from the log because of retention, we would return the unknown producer ID, we would bump up the epoch, reset the sequence, and continue on. That was the idea. There's a link here to more about this specific work. However, even though we had this plan and it sounded good, there were still a few issues. Sometimes unknown producer IDs still led to more confusing scenarios. I mentioned that we reset the epoch and we reset the sequence, or we bumped the epoch and reset the sequence. But there were some ambiguous cases where maybe we don't know if a record was written. If we bump, the epoch and reset the sequence, we don't know what happened to that data. Maybe there was a timeout and we don't know if it was written or not. And, that's not great for exactly one semantics. And there were also still some fatal cases with unknown producer ID. We originally didn't want it to be fatal, but there were some cases that still came up. We also had some problems still with the out-of-order sequence errors. So even then, it sometimes didn't represent real data loss when there was a leader failover and the follower might have had slightly out of sync state. So again, we had to go back to the drawing board. This is where KIP 360 comes in. This was another overhaul to the idempotent producer. So the first thing that this KIP introduced was safe epoch bumping. So that issue earlier where we didn't know whether or not the epoch bump was correct and whether or not we should just reset the sequence, this JIRA tried to address that case. The unknown producer ID error became rare and abortable and never fatal. And if you look at the code today, this error is actually removed completely. We still handle it on the client side if a Kafka cluster still returns it to the client, but the newer clusters today actually don't return this error anymore. And instead, we often accept non-zero sequences in most cases. So if we don't have any producer ID state on the broker and a sequence comes in that's non-zero, we'll just go ahead and accept it. And this kind of can introduce an issue where maybe on the first time we write to a topic, it will not write let's say we have like a sequence 5, right? We'll have 5 need to be retried with a retriable error, and sequence 6 will come in. If sequence 6 is written, sequence 5 will always be blocked, out of order sequence error, and we'll keep retrying. This is not a huge problem on transactional producers, but it is a pretty big problem for our idempotent producer, and so we hope to tackle that in the future. The other thing that KIP 360 brought about was storing producer ID state for longer. So previously I mentioned that we store all of the producer ID state on the data partition, and we will reload it in whenever we need to the broker. And previously this was always the case that if it was on the broker, it was in the memory. But KIP 360 introduced a new change where basically we would always store it in memory as long as we could. And this sort of introduced unbounded memory potential. So I quickly want to go over KIP 484 and slow loading. I mentioned that we store a lot of the state on disk for the transaction coordinators in the state partition, and this state partition metadata is loaded when we elect a new transaction coordinator or when a broker starts up. Every time we reassign, we'll load from the disk. And so if there's more data on the disk, it will take a lot more time. And so we were seeing some issues with a lot of state on disk, and we wanted to fix it. So we introduced a metric just to see what was going on, and we could compare before and after for any performance improvements. Next KIP I'd like to talk about is KIP 691 with error handling. When transactions were first introduced, there was some confusing errors, some error handling that was not consistent. You've probably heard me speak of it already. And the idea with KIP 691 was we wanted to introduce consistent error handling. So once the client receives an error, it's pretty clear what they're going to do with it. If it's retriable, if it's abortable, if it's fatal. But this KIP has met a few roadblocks. It is accepted, but there are some issues with compatibility versus consistency. So as you may know, in Kafka, we try to maintain compatibility across all versions. And this can introduce some, difficulties when you're trying to make changes to older error codes or how we handle those error codes. So sometimes there's a little bit of a conflict between compatibility and consistency, and that's something that we need to work out. Okay, so returning back to the idempotent producer saga, KIP 697 established idempotency as the default. So now any Kafka producer will automatically, by default, be idempotent. There's one issue with this, and that's that sometimes certain users may spin up one-time use producers. These producers will be very short-lived. Maybe they only write like one message, and then they're gone. But the problem is, earlier at KIP 360, we said that we would hold on to this producer ID state basically for a while. And storing too much of this producer state will actually cause out-of-memory issues on your cluster because we just have so much state. And when this KIP was first introduced, the KIP 679, the transactional and producer ID state expiration used the same configuration. So it was the transactional ID expiration milliseconds. And that default was 7 days. So basically, we would maintain in memory until we hit that 7-day mark, and then we would expire them. It was decoupled from the actual removal from the log. It's possible, since they're the same value by default, they would be about the same, but they were actually two separate configurations. So one idea that came about was, okay, if we have this transactional ID expiration config, maybe we can just reduce it so that we don't have to worry about these out-of-memory issues. But the problem there is that if you just go ahead and do that, the transaction metadata expiration can trigger these invalid PID mapping errors that can be fatal. And we don't necessarily want to remove that transactional state. So one solution that we came up with was introducing a separate config for the producer ID state. And so KIP 854 did just that. KIP 854 only affects the producer ID state in the data partitions. It doesn't touch the transactional metadata and the transactional state. And the default for KIP 854 is 1 day of storing the producer ID info. And basically how this helps with the case I mentioned before is that now if we have these one-time use producers, we will expire them much more quickly than we did previously. And hopefully that can help with the out-of-memory issues. Okay, I'm going to shift back over to transactions now, and I wanted to talk about hanging transactions. So some of you might wonder, what are hanging transactions? You mentioned before that once you hit a certain amount of time, we'll just automatically abort. How can we have hanging transactions? Well, this is how it happens. You might remember that the transaction coordinator sends markers to all the added partitions in the transaction. But what if a partition wasn't added to the transaction? And you might wonder, how could a partition not be added to the transaction? You just told me that that's what the producer does before producing to any partition. Unfortunately, there are a few edge cases where maybe this can happen. One example is maybe there's a client that's a little bit buggy and somehow it didn't add the partition to the transaction. Another thing I've seen quite a lot now is that there are a few race conditions where maybe we were in a transaction and we were sending a message to be included in the transaction, but just before it was sent or just before it was received, we actually wrote a commit marker. In this case, there are a few times where we've seen actually the produce request come in after the marker. And at that point, if we don't ever, write to that transactional ID again, we'll never write another marker for that record that was written. And so why is that an issue? When this happens, the last stable offset gets stuck. Let me quickly explain what the last stable offset is. So the last stable offset is the first offset of an uncommitted transaction in a partition's log. So here's a little demo to explain. Let's say we started a transaction with producer ID 2 and with sequence number 0. The last stable offset is the offset of this record. We'll continue producing as part of this transaction, write sequence 1, and then we'll commit it. At this point, the last stable offset moves to this commit marker because there are no uncommitted transactions in the log. It's just the log end offset. Let's say we start again, then the last stable offset moves up, and maybe we wrote another, with another transactional producer to the log, producer ID 5. We continue producing, and when we commit with producer ID 2, the last stable offset actually moves to the first offset of producer ID 5's transaction. That's because even though producer ID 2 is committed, the first record in the log that is part of an uncommitted transaction is producer ID 5's sequence 0 record. And we'll continue writing. Maybe we start a new transaction with producer ID 7. Once we've written 5, we'll bump it all the way up to the first uncommitted record in the log, which is now producer ID 7. Okay, so last stable offset gets stuck when we are writing a hanging or when we encounter a hanging transaction because we never see that commit marker that moves it up. But why does that matter? When you're writing transactions in Kafka, you're often going to use read committed consumers. And read committed consumers are only reading committed transactions in the log. Normal consumers will read all of the data, even the uncommitted records, but read committed only reads committed records. And the read committed consumer can't read past the last stable offset. So looking back, when we had this scenario, even though producer ID 2 had a committed transaction, we can't fully read this transaction because the last stable offset is in the middle. So it's something to keep in mind that even if your particular producer ID transaction is completed, if there's another transaction ongoing that's blocking the last stable offset, you won't be able to read your future records, even if they are part of committed transactions. The other thing is that if this was a compacted topic, the log cleaner can't clean past the last stable offset. And what this results in is very large partitions with a lot of data. I mentioned earlier how the transaction coordinator has a state topic. The consumer offsets is also a state topic that's compacted. So if we have a hanging transaction on the consumer offsets topic, we have another state partition that can grow very large. And when a state partition is very large, any broker that comes up and needs to read that state partition will take a long time. And this is potentially pretty bad. So hanging transactions are a pretty bad issue, I think. Well, what are we going to do about it, right? Let's talk about KIP 890. So there are two parts to KIP 890. In the first part, we want to eliminate hanging transactions on all clients. I want to call out all clients because it was a specific design decision that we wanted to address old and new clients for this KIP. I think it's really important that we address both the new things incoming, but also the existing, situation that we have. And the thing that makes this tricky is that in order to address it on all clients, we need to be compatible with all clients. And that means that we can't really have any client-side changes. And so what we did here is that we introduced an extra interbroker hop when we try to produce to a partition for the first time in a transaction. This extra hop goes and asks the transaction coordinator, hey, have we added this partition to the transaction? If yes, then we can go ahead and write to the log, and if no, then we shouldn't write it because we might create a hanging transaction. We also do a second check right before writing to the log to ensure there's no race condition where maybe a commit marker is written at the last second. But the issue with part one is that we can still add records to the wrong transaction. We may have a record come in that belongs to a previous transaction, and a new add partitions request come in, and we see that it's been added, but it's actually for the new transaction, and that old record is absorbed into the new transaction. So there's still a few gaps in the transaction's correctness, but we do get rid of the hanging transaction issue. How are we going to fix this correctness issue? Well, that's where part two comes in. So part two also includes client changes to strengthen EOS. We first want to remove that extra interbroker hop, and so when we produce to a transactional partition, instead of the producer requesting the add partition, we'll have the broker that's receiving the request do an interbroker call and add the partition. And that way we can never write to a partition without it adding to the transaction. How we cover the second bullet point here, where maybe we've added the partition to the record to the wrong transaction, is that we actually want to introduce an epoch bump on every transaction. And what this accomplishes is that the epoch plus the transactional ID will uniquely identify a transaction. And we can ensure that every record written in the transaction belongs to the one that it should. This epoch and transactional ID change also it unlocks other cool use cases. So previously, when we had transactions, we didn't actually know which records were part of which transaction. We would just see records in a log and a commit marker. And when you were looking at two partitions, you wouldn't know. You could look at the producer IDs maybe, but the epoch may stay the same. So you don't know which transaction both included those records. But with this epoch and transactional ID, epoch bump change, now when you look at the partitions, you'll see the epoch number and the transactional ID, and you'll know all of those records with that epoch and transactional ID were part of the same transaction, which is pretty cool. I quickly want to go over KIP 936. So as I mentioned earlier, we had the whole situation where we have maybe a lot of producer ID state and we want to expire it more quickly, so that way we don't run into out-of-memory issues. There are some questions about whether or not expiring that state could lose idempotency guarantees. So when we remove the state, we will no longer be able to check those sequence numbers to ensure that we have our ordering and no duplication. And ideally, we don't want to expire state too soon and lose those guarantees, especially for well-behaved clients that are still using them. So one suggestion is maybe we could throttle on the creation of new producer IDs in those cases where there's maybe a bad client that just is spinning up multiple producers. And there becomes this kind of struggle between availability of correctness here. Because on one hand, if we start throttling new producer IDs, we're potentially causing availability issues for those new producers who may be, good actors and doing the things that they should be. But on the other hand, we might lose correctness for the older producers that were behaving and maybe just need their state stored longer. So there's kind of a balance there, and I think it's up to users to decide whether they, prefer the producers to stay up and running, or if they prefer, pure idempotency guarantees. This KIP is still in discussion, so if you're interested, please discuss on the mailing list. And yeah, I guess to be clear, I think the main question is like, how do we identify the misbehaving clients? Ideally, we don't want to punish the producers that are behaving as expected and aren't spinning up a lot of new producer IDs. KIP 936 proposes that we throttle by the user as part of the request. But I think this kind of exposes one of the issues with the idempotent producer in that when we have a default, we're automatically assuming that we know this use case and that we're going to have this producer that wants to produce a long time. And maybe we need to adjust some things to have the system run as expected. So if we were creating idempotent producer v2, what would we want it to look like? Well, first we want clear semantics. So we want the ordering and no duplicates, as we mentioned, for idempotency. The next thing would be bounded memory use. So instead of having this producer ID state that can grow without bound, we would want some way to prevent that. And some ideas there is that maybe we could have a contract between the client and the server and say, if you are a client and you want to use producer ID, you need to periodically, check in with the server and say, hi, I'm still here. Please keep my data. Another idea for bounded memory usage is maybe something like an LRU cache, where the last thing we've seen, we expire the last thing that has, oh my goodness, an LRU cache where maybe the data that we remove is the data that was least recently used. Another idea that would be cool for idempotent producer v2 is maybe idempotent producer could exist across sessions. Right now, it does not. When we have a new producer come up, it starts at sequence 0 again, and there was no notion of its previous state. But maybe if we had an idempotent producer v2, it would be cool to think about if it could be used across sessions. Okay, so kind of finishing off the talk today, I want to quickly go over KIP 939 and the future of two-phase commit in Kafka. You all probably saw this in the keynote this morning, but I'll quickly go over it. So what if you have an outside system, like a database, and you also want Kafka to stay in sync with it, and you want to use transactions? One great solution for that is two-phase commit. And so in two-phase commit, you have a prepare phase where all the participants either say we're ready to go or no go, and then if everyone's ready to go, then you commit. Kafka sort of does this implicitly internally right now. So when we are producing to our partitions, if we see an error, we will abort the transaction, and it's kind of like the no-go. But if we flush the data to disk and there's no errors, it's kind of like an implicit prepare. And so once we are ready to commit, the transaction coordinator sends all the markers. That's the commit phase. But maybe we want to extend this idea to external systems like a database or, I don't know, Flink. How can we do that, right? Well, KIP 939 introduces some explicit API changes that allows us to explicitly enter a prepare phase where perhaps if the producer goes down and comes back up, we can resume either with the abort or commit. So there's also flip 319 for Flink to use the Kafka two-phase commits in coordination with KIP 939. In the session in this room after lunch, Gordon and Alexander will be talking about this flip in more detail. And so if you want to learn more, I highly recommend their talk. All right, so since it's the end, I thought it would be very fitting to put a commit marker at the end of my talk. So thank you all. I hope you enjoyed.